Okay, in this video, I'm going to show you how to set up Fluent for our simulation of the cooler. The first step is to import the mesh, is to read the mesh into Fluent. Here, of course, you can just read the mesh and so on, but I will directly read my case file. Okay. After you read mesh into Fluent, the first thing you want to do is to check the mesh quality. Okay. Here you should not see any error message, warning message, those things. Then if you want, you can display the mesh, although it doesn't really do anything for you. Okay, it's just such a big box. When you created your mesh in ICEM, you probably want to use the SI unit. What I mean is you use meters for length. But in any case, if you used some other unit system like using feet or some other stuff like millimeters, centimeters, you will have to scale your model in Fluent. Okay, this can be done here, scale. Then mesh was created in, for example, centimeters, millimeters, inches, feet, those things. If, for example, your model was created in ICEM with using centimeters, okay, as units. Okay, so for example, the side length is 1, which means 1 centimeter, right? Then you will have to scale, okay, you push this button, scale, to convert it to meters, like 1 centimeter is 0.01 meter, right? Okay. Of course, we have our simulation, in fact, is a transient heat transfer process. Everything changes with time continuously. So you have to select transient, and gravity effect is very significant because natural convection indeed is caused by the density variation of the fluids and the resultant gravity force variations, right? So you have to set up your gravitational acceleration here. Notice that the positive y direction is pointing upward, so the gravitational acceleration in fact is negative. Okay, it points downward. Okay, in the models, you have to turn on the energy equation for obvious reasons, right? Because we are going to calculate the temperature, distribution, which are solved from the energy equations. Here I assume that the natural convection in the whole setup is in the whole computational domain is laminar. This may not be correct. Okay. It really depends on the so-called Rayleigh number. Rayleigh number. Okay, RA. Just check your heat transfer textbook or simply Google this number, okay, and find out how to calculate the Rayleigh number and find out the criteria for the natural convection to become turbulent. Okay, so when such transition from laminar to turbulence occurs, okay, it always occurs at a certain critical Rayleigh number. So you should first do some preliminary calculations to give a rough estimate of the range of the Rayleigh number in this whole process. And if that Rayleigh number is higher than the critical value, then here you have to change this model from laminar to some turbulent model. Okay. For example, you can use the SST K omega model, which usually is a good option. But if the Rayleigh number is less than the critical Rayleigh number, you use laminar flow model. We don't need to use other models here. Materials. Here we will not only simulate the motion of the fluid flows, like the motion in the air inside of the room and inside of the cooler, and the flow in the water inside the cooler. We also have to solve the energy equation for not only the fluids but also the solids, right? Like the insulation layer of the cooler, aluminum container, those things. So here you in fact you have to define many different types of materials, okay, which will be used in our simulation. So by default, the fluid material is air, so we don't need to okay, air okay, this air, its default setup is a constant density, okay, which is not good for our purpose, because we will simulate natural convection, which is only possible when the density is changing, right? It varies from one point to another point. So change this density from constant to incompressible ideal gas, which means ideal gas law will be used to find the density, okay, but the pressure will be maintained a constant. So if you think about ideal gas law, right, which is pressure equals density times gas constant times temperature. So if pressure is maintained constant, then density in fact is only affected by temperature, right? So this is what this model does for us. If we want a really accurate simulation in the future, we will also have to use, variable Cp value, conductivity value, viscosity value, those values. But here I don't do that. Okay, I simply, assume constant values for those properties. Okay, then you have to add this liquid water as a material in this fluid category. Okay, this can be done by right-clicking fluid, then click New, then change this name of the material, right? For example, you can call it water, but here in fact you don't even need to do that, because liquid water is one standard material in the Fluent database. Okay, so you just click Fluent database, Then go to the very bottom of this list. You will see liquid water here. Okay, just click here, then click copy. Then this liquid water will pop up. Okay, it will be added into this material list. Again, the default setting is a constant density for water, but here since we will simulate natural convection of water, so the density of water cannot be constant. But since liquid water, again, is not ideal gas, right? Its density, in fact, changes with temperature with a pretty complicated relationship. So here I'm using a piecewise linear distribution of density. So you first select, piecewise linear, where it is. Okay, here, piecewise linear, right? Then it will ask you to input this density versus temperature distribution. Okay, you can select as many data points as you wish. Here I used like 7 data points. Okay, that's probably not good enough. Okay, you can see my density versus temperature curve is not very smooth, right? I suggest you to use more points. Okay, maybe like 30 points. So you can manually input, those density values at different temperatures. And notice that temperatures are in Kelvin, okay, not in degrees Celsius. So it will be the best if those data points you use here covers the whole range of covers the whole temperature range involved in our simulation. Because the water inside the cooler was originally at maybe 4 degrees Celsius, right? So I think it will be the best if your temperature range goes from like 0. Maybe even goes from 0 degrees Celsius. Okay, of course that is a cold water, ice cold. So goes from 0 or 1 degree Celsius, then 2 degrees Celsius, 3 degrees Celsius, all the way to like 30 degrees Celsius. Okay, but remember to convert those Celsius to Kelvin and their corresponding density values. Okay, those values definitely can be found on internet. Okay, then remember to click this button. Okay, change create. Then all those numbers set up will be there. Okay. And again, the CP value, conductivity value, viscosity value, in fact, are not constants. They also change with temperature. So here, in the future, if we do more accurate simulations, we probably also want to change all of them to piecewise linear distribution. Okay. So similarly, you want to add a few more materials into this solid type. Okay, the default material, solid material, is aluminum. You don't need to change that. Indeed, we have an aluminum container inside. We need that, but we also need the material for the insulation layer, right? I call it foam, and the water is in a plastic bag. So I add another material called a plastic bag, and there is some gaps, right, in between insulation foam and the aluminum container, right? Because those two surfaces are not perfectly smooth, there are always some gaps, in between them, and air present in those gaps. You can see that I add air in gap as a solid material. The reason is because if you use air as a fluid, okay, anything any fluid in fluent will have to, okay, if you assign any computational zone as a fluid, okay, you assign a fluid material to a zone, then what happens is that the Navier-Stokes equation will be solved, okay, will be solved in that zone. But for the air in those small gaps between two contacting materials, contacting surfaces, right? The air indeed is almost stationary. Okay, they do not flow. Even they are flowing, we do not know the detailed, the details of those gaps, right? We do not know how they look like, the geometry, those things. So indeed, by no means can we really simulate the flow in air in those gaps, right? So we have to treat those air in gap as a solid. Okay, they do not flow. We do not solve the Navier-Stokes equations for their velocity distribution in such air. Okay, they are treated as a solid. So to add a material to solid, again, you have to right-click it and new, then give it a name, say air in gap, and the material type is solid. And remember to delete the chemical formula here. The default formula is Al, which is aluminum. It's not aluminum. You don't need to type the name here. It will automatically filled by Fluent. You only need to provide the density. Okay. In fact, even the area in the gap, its density is not constant, right? It's changing with temperature. But here it's not very important. Okay, for this density variation is not important because even its density is changing, but since we do not care about the flow in the gap, right? In fact, air almost doesn't flow in such gaps. So the density variation, in fact, does not really affect our calculation. We only care about the solution of the energy equation, the temperature distribution across such gaps. So it's in fact more important to have an accurate CP value, thermal conductivity value, those values. Okay. Here we again treat them as constants, which probably good enough, okay, because they do not really change much with temperature. But if you really want a super accurate simulation, you will want to change them to like piecewise and linear, those kind of stuff. Okay, then after you input those properties, by the way, for those properties you want to find accurate values. Okay, what I mean is you want to search internet or your heat transfer textbook appendix tables to find out how much is the air density in the temperature range, right, involved. Then you push this button, okay, change, create. Then a window will pop up. The window asks you, do you want to override the original aluminum material, you should choose no, okay, because you want to keep the original aluminum material. You only want to add this new material into the list. Okay, then similarly you add the foam material, right, for the insulation. Those numbers I put here are from Google. Okay, the Google only gives me a range of density and CP value conductivity, so I kind of randomly pick probably the mean value of those ranges. Okay, the mean values of those ranges. I guess you know what you should do, right? You should really find out the accurate density of the foam and its CP value and conductivity value. I don't know how you get those values, probably from the manufacturer. Anyways, yeah, you have to find more accurate values from a reliable resource, okay, from a reliable source. The plastic bag, again, those values are found from internet, not necessarily accurate. You probably want to have more accurate values. Okay, once you have those materials, you can assign different zones of the computational domain with different materials. Okay, so cell zone conditions. You may find that we defined like 5 zones, right? Like the air in the cooler, the air in the room air, water in the cooler, the aluminum container in the cooler, and insulation. Fluent may put all those zones under either fluid or under solid. Okay, you will want to move them to the appropriate category, right? This can be done by right click, okay, a zone, then change its type. Okay, it can be changed from solid to fluid or vice versa. Once you did that, then you can double click this zone and change its material. Okay, if it is a fluid, then now you have 2 choices, right? Either it's air or liquid water, and so on. Similarly, you change the material for the solid zone, right? Now you have lots of different materials. Okay, after this is done, go to boundary conditions. You don't need to worry about those internal boundaries, but you do need to set up the boundary conditions, the other types of boundaries, right? That's why we define so many faces, right? Because then you can apply different conditions to different surfaces. Okay, for the foam bottom, I don't know if I can show you. Okay, where is the foam bottom? Okay, close. Why it doesn't close? Where am I? I should be here, right? Okay. Yep. Okay. This is the bottom of the foam. Okay, that is the bottom surface of the cooler. I directly set it as I set it with a constant temperature. Okay, 300K temperature. In fact, this temperature probably is too high because that is about like 80 degrees Fahrenheit. Okay, probably not very realistic because we will want to compare our results with those experimental data. And experiments take place in the biolab, right, which is air conditioned. So temperature is much lower, I believe. Here you can see that even for this surface, you can define its material name. Okay, what it means is that you can attach one layer or many layers of material to this surface. So because this surface, in fact, you know, in the real world, of course, this cooler is resting on the ground of the lab, probably, right? And I will assume that the ground has a constant temperature of like 300 Kelvin. But the bottom of the cooler does not have perfect contact with the ground, right? They do not just attach to each other without any gaps. They have gaps. So in those gaps, we have air, right? So there is an air layer, attached to this bottom surface. Okay, so the ground is at 300K. Okay, but the bottom surface of the foam probably is not at 300K. This is what it means. Okay, there is a air layer attached to this surface, and I assume that this layer, its thickness is 1 millimeter. That is 0.001 meter. In the future, we can change this number. Okay. Yeah. If the contaction is pretty good, then we can reduce this thickness of air gap. If the contaction is not good, okay, the cooler surface is rough and the ground also has lots of roughness, so there are big gaps, right? Then we can increase this thickness. Okay, the side surfaces of the foam, okay, is simply a coupled condition, okay, which means I do not give it any conditions. Okay, I do not specify its temperature. I do not specify the heat flux across those side surfaces of the cooler, right? Because those will be calculated. Okay, it's part of the calculation. The air is flowing right around this cooler because of the natural convection, and that causes heat transfer between the air and the cooler material. So that is what the coupled means. You may ask me, right? Why do you not add like air in gap, those kind of things here? Because here you don't have any gap. Think about that. Okay. The foam is in direct contact with the air in the room. That makes sense. You don't need to add air in gap here. Okay, you do not have two solid surfaces in contact in this case. Once you set up this side, then the side shadow will be automatically set with the same conditions. Okay, so you don't need to worry about that. The same is for the top surface of the foam. Okay, air, aluminum. Okay, that is the surface here. Say this is an aluminum container right here. Here you still have some air above this container and also inside part of this container. So you want to set up the condition at this interface between air and aluminum. That's pretty much the same as the interface between the room air and the foam, right? So you still use coupled. The material name is aluminum, but in fact here, no matter what kind of material name you use, it doesn't matter, okay? Because its thickness is 0. Okay, there's nothing here. It's just the interface. Okay, so it's yeah. This is what it means. Okay. Okay. Same thing here. Okay. Here you can see foam and aluminum. Right. The interface between foam and aluminum. That is such an interface like this one, right? This is foam and this is aluminum container. So we assume that they are contacting with each other without any visible gaps at such an interface. Okay, in fact, the contaction is not perfect, right? There must be some air, here and there in those bumps or valleys along the surface. So I put one layer of air, okay, at such a surface, and I assume its thickness again is 1 millimeter, and in the future we will want to change the thickness, okay, to fine-tune our results until results match our experimental data well. Okay, I don't need to talk more on those boundary conditions, I believe. Then that's pretty much we need. Then we will initialize, right? We will initialize I guess did I change that? I didn't change that. I probably want to change that. Okay. The residual monitors. And here you can see you can set up the criteria for the iterations to terminate, because Fluent uses iteration method to solve those energy equation, the Navier-Stokes equations, which are these 4 equations, right? But those iterations eventually have to terminate, right? You cannot net it to iterate forever. So those numbers are used to determine when the iterations should terminate. Okay. Basically, if the residue is less than this number you put here, then the corresponding equation will be considered as being converged. Okay, you have already got good enough results from that equation, and then Fluent will no longer continue solving that equation. So here, one danger is that this number is too big, so even you still do not have good enough results, Fluent stopped, okay, iterations. So it's probably good to set a pretty small number for the continuity equation. Just make sure that Fluent keep iterating, okay. In fact, you can always, manually stop its iterations. So don't worry that it will do the calculation, without termination. Okay. Then you want to initialize all the variables in the simulation, like pressure, u velocity, v velocity, w velocity, right, or x, y, z velocities, and temperature. Okay. Those iterations have to begin with some known values or initial values. Okay, so this is what this step does for us. We gave some initial values for those variables. Okay, and don't worry, those initial values typically do not affect the final results. Okay, they just gave Fluent something to begin with. Okay, something to begin the iterations. Of course, if those values are very close to the final accurate results, then Fluent will only take a few iterations, then it can give you the final results, right? So, although it does not affect the final result, it does affect the time Fluent takes to get those accurate results. So, it can be calculated from anywhere. Then you push initialize, then the whole domain, okay, the variables in the whole domain will be set to those initial values you put here. But here you should remember that although initially, I'm sorry, here in fact initial values are important, okay, because we are doing a time accurate simulation. So we do need an accurate initial values for pressure, velocity, and temperature. Okay. So here we assume that initially, when we first put the water in the cooler and put the cooler in the lab room, the air and the water do not move. Okay, the natural convection just begins. So the velocities are all zero, the gauge pressure is zero, and the temperature of the room air, the cooler, container are all 300 K. Okay, except that the water temperature definitely is not 300 K, right? The water here, it is refrigerated to like 4 degrees Celsius. So once you push this initialize button, then the temperature everywhere, including in the water, will be set to 300 K. So then you want to change the temperature of the water, and only the water, okay? The rest is indeed at 300 K, but water is not. So you want to change the water specifically to a different value. This is done by using patching, okay? Patch. Then you select this water in cooler zone, okay? Select temperature to a different value, say 277, which is 4 degrees Celsius. Okay, then click patch. Okay, patch. Click it. Okay, although here I didn't click it, but you should. Okay, click it. Then you will say that the temperature okay. Here is in fact not the not the initial value. Okay. Okay. What did I do here? Okay. Anyways, let me do it again. Once you do it, do the patch correctly, you will see that the water region is at 277 degrees and the rest is at 300K. Okay. Then you can do your calculation. Okay, it's very simple, as you can see. You can set up the number of time steps, and each step is like 1 second. Okay, I'm not saying that 1 second is perfect number. Okay. If you want a really accurate simulation, probably you want to use a smaller time step size, maybe like 0.5 seconds or 0.2 seconds. And each time step, the Fluent is going to iterate for 20 iterations. And again, this number is not necessarily perfect. Okay, you probably want to use like 30 iterations or even 50 iterations. Okay, once you have those numbers set up, then you can push calculate button. Here, of course, it will do the calculation for us, right? And you will see that the temperature in the cooler will begin to change with time, right? And as time goes on, eventually the temperature in the room air also will change with time. But you want to, keep a record, right? See how the temperature changes with time. So, before you push this button, okay, before you push this calculate button, you probably want to here, I believe it's here, calculation activities, using maybe autosave, to save your data for to save your data per every some time steps. Okay, you can choose like every time step, but that probably give you lots of data fail. Okay, you can choose like every 10 time steps, okay, or like 20 time steps and so on. Yeah. And I believe you also can report delta time. What is that? Probably it's not this one. Something. Yeah. Report definitions. New. Yeah. Surface report. Mesh report. I forget. Okay. Anyways, yeah, just play around here. Okay. Report, monitor, those stuff. You should be able to give you, for example, the temperature at the very center of the water region. Okay, it will be able to monitor how its temperature varies with time. It also can monitor multiple spots. Okay, for example, another point in the air region, in the cooler, in the aluminum container, in the foam, right, and in the room air. You can set up a bunch of different monitoring locations, and monitor how the temperature varies with time. Okay, this is the end of the tutorial.